you should start doing something, right? That's why you're here, I hope, doing something. Otherwise, that would be kind of waste of time. If this would have been a Carnot cycle, an ideal cycle, all we would need to know is the highest temperature and the lowest temperature, and done. To calculate those temperatures, we would have to apply the ideal gas law 4 times for state number 1, 2, 3, and 4. Choose the number with the highest temperature, choose the number with the lowest, and done. But this is not the Carnot cycle, so we cannot use Carnot equation. We have to do it step by step, and now we can just do it. For each process, we can apply the same set of equations, plus for the whole cycle, what equations can we apply for the process? Q equals delta U plus W. W is equal to area. Delta U is equal to I over 2 nRT delta T. These are the most important, the fundamental equations. The last one assumes that the number of moles, the amount of gas, remains constant. We also have 4 states, 1, 2, 3, 4. And for each state, we can write the ideal gas equation for each state. So 1, 2, 3 times 4, 12, plus 1 times 4, 12 plus 4, 16. 16 equations can be used. There is no problem in the world when we would have to use all 16. It's more like 5 or 6. But which one? We don't know, usually. So we have to pick up and just start. And normally, it would have been either this, or this, or this. Yeah, these are fundamental ones. Well, let's do work because we started from work. 2, 3 has to be equal to. So I saw some people being confused about the situation when they did homework problem. For the process, not for the cycle, for the process, the work is equal to the whole area from the V-axis to the process. So it's going to be P2 times delta V. This is delta V. V1, V4, delta V. So someone wants to trick us. We don't know P2, but we know P3, and the graph tells that they have to be equal to each other because that's a process with constant pressure. So we can use this number, 400 times delta V, 20 minus 10, 4,000 joules. 4,1 will be equal to P1 times delta V. See, I'm writing the equation always the same. But when I start using that equation, I have to see the difference. P1 has a different value, and delta V will be equal to now 10 minus 20, because that's what delta means. Final minus initial. If you forget that, you get a wrong number. And you can see again that when gas contracts, the work has to be negative. So we have negative 2,000 joules. That gives actually total work over the cycle, 4,000 minus 2,000, 2,000 joules. Okay, perfect. That's first part of the efficiency. The efficiency is equal to the work over the cycle divided by the amount of heat absorbed by the system, 2,000 over Q. Now we know what to do next. We need this, we don't know this, we have to find this. This is related by other variables by the first law of thermodynamics, so we gotta do that. How many times? Well, as many as we need. We need to check all processes, so Q12, delta U12 plus W12, which is delta U12, because for this process there is no work. It happens at constant volume. And that will be equal to, well, I don't like this equation. I have no information about temperature. I could find the temperature, but I don't want to. Instead, I want to use a different equation. U equals I over 2 PV. Because I can replace this product, nRT, with that product, PV. And in this situation, the volume remains constant, so it's a common factor. It's a monatomic gas, I equals 3, so 3 over 2 delta PV. Only pressure changes, and that gives me 3 over 2, 400 minus 200 times 10. 400 minus 200, 200, 200 over 2, so 3,000. Positive. Good. That's the first part of QH. Next process. Again, we do it only just to review the whole topic we've studied for 2 weeks. This one problem includes almost everything. So, delta U plus W. This is a special process happening at constant pressure, which is good because for this process, we know the relationship between delta U and work, I over 2 W plus W. So 3 over 2W plus W, 5 over 2W, and this W was found before 5 over 2 times 4,000. 4 over 2, 2 times 5, 10 joules. Also positive, so another part. I told you once, our mind always plays tricks on us without our knowledge, so we have to be alert. And there is a work done during a process, there is a work done in a cycle, different. This is for the specific process. I'm not going to do the rest. If you do the rest, that's a good exercise. Those two processes happen with negative Q. And so if you want to calculate the only amount of heat absorbed by the system, we just have to add these two. 3,000 plus 10,000, 13,000 joules. Now we have everything. That's going to be 2,000. That was the work done in one cycle over 13,000. We can multiply by 100%. Done.